Hi, this is Sholey Physics episode on applying Ampere's law. As an example, I'm going to use a question from University of Physics by Young and Friedman, 11th edition. I enjoyed this problem, and I think they took it out. Maybe not in the newer editions, but a magnetic field of 37.2 Tesla has been achieved at the MIT Francis Bitter National Magnetic Laboratory. Find the current needed to achieve such a field, 2 centimeters from a long straight wire, at the center of a circular coil of radius 42 centimeters that has 100 turns, and near the center of a solenoid with radius 2.4 centimeters, length 32 centimeters, and 40,000 turns. So I'm not just going to pull out the magnetic field around a straight wire from the textbook or the magnetic field at the center of a solenoid. I'm going to use Ampere's law to work this out. And I really encourage you as a training physics student here to actually do these yourself also. Don't go to the shortcut. Take the time, solve the problem. And that's how you're going to get to know it a lot better, by using it. So we're given a magnetic field, strength of 37.2 Tesla, and we're looking for the current in each case. Okay, A, we've got a straight wire. There's our conductor. Whether it's straight or not, that's up for discussion. We're looking at a position 2 centimeters from it, so it's a long straight wire that the length doesn't matter. We are at a position R of 2 centimeters, and this is where we're going to start. Okay, so we got this wire, and thinking about a region where the magnetic field is constant throughout, I'll define the current I. There we go. So anywhere around this wire at distance r, the magnetic field should be the same. Using the right-hand rule, current's going this way, the magnetic field has a kind of a curling pattern around it. So magnetic field here would be this way towards us, away from us, to the left, to the right. And that magnitude of the magnetic field should be the same. So first thing I'm going to do is write out Ampere's law. B dot dl equals mu naught times the current enclosed. Okay, nice one on this one is the current enclosed is the current going through the wire. So to start with, my loop I'm going to take around it is at 2 centimeter radius, and that loop is just the circumference. It's the length of that loop. So the sum of the closed loop dl is 2 pi r. So we're going to have a b times 2 pi r is the length around there. Now if you really want to get technical, you can plug in r theta here, and we're going to go from 0 radians to 2 pi radians, and that's how you would integrate the whole thing around there. So it's another way to look at it. And the I enclosed is the I that we're looking for. So the magnetic field, using Ampere's law, is just mu naught I over 2 pi r. All right, we're going to use 4 pi times 10 to the negative 7 for our mu. I is the unknown. 2 pi is there, and the r is 2 centimeters, so 0.02 meters. So a little simplification here. I think I can do this one without too much problem. Our 2 pi and 4 pi and 2 pi cancel, except that leaves us a 2 up here, and 2 divided by 2/100ths, 100. So we're going to have an I times 10 to the negative 7 divided by, so it would be times 100. Now we can plug in the B, 37.2 Tesla equals I, and 10 to the 7 times 10 to the 2 is 10 to the negative 5. Divide both sides by 10 to the negative 5, and we get our current. This is like multiplying by 10 to the 5th, so 37.2 times 10 to the 5th power, or 3.72 times 10 to the 6th amperes. So you can use mega amperes if you want. All right, there we go. That's the letter A. Letter B. At the center of a circular coil of radius 42 centimeters that has 100 turns. So here, all right, let's take that circular coil. Okay. Usually the coil is going to have little leads that go off to attach to give us a current. All right, so I'm going to have my current going around this way. We've got a radius of 42 centimeters. So that's 0.42 meters. Go ahead and convert that. And we've got 100 turns. Now in this scenario, you won't be able to use Ampere's law. You're going to have to go back to using the Biot-Savart law. Now the reason is, if we take a loop like around there, we're only really looking for the magnetic field specifically at the center. We're not looking for it way out here. The magnetic field out here is going to be different than it is in here. That's different than our last scenario where the magnetic field was constant, or I should say consistent, all the way around that circumference at a radius of 2 centimeters. So there's no loop that we could really define here that has that kind of symmetry. So I'm going to reference the hi kitty. His name is Edge, after the Final Fantasy character, Final Fantasy 2, also Final Fantasy 4 on Game Boy or something like that. Yeah, Game Boy Advance, I think. Final Fantasy 4, it's a good game. Anyway, the magnetic field at the center comes down to mu naught times n number of turns times I divided by 2 times that radius, I believe it is. Okay, 2 times that radius. So we're going to have 4 pi times 10 to the negative 7. In number of turns, we've got 100 turns. The current I is what we're looking for. It's the unknown. 2 times 0.42. There it is. So again, we're trying to achieve a strong magnetic field here. 37.2. So we get a 1.495, I'll say 1.50 times 10 to the negative 4. So that's 10 to the negative 1.5 times 10 to the negative 4. We're going to divide by that on both sides. $37.2 divided by that answer. And we get a whopping big number here. Cat. Ow. Ow. He's got claws on my legs. Ah. Thank you, child. Thank you for taking me away. Okay. And we get a whopping 2.49 times 10 to the 5 amperes. Okay, so 249,000 amperes. Better, but still that is a huge current. That's a problem, actually make something like this. So that is a massive current. To get a wire to carry that current, would have to be pretty much super cooled. All right, so last one, last scenario. Let's go back to MIT here. What if this was a solenoid of radius 2.4 centimeters, length given, and 40,000 turns? So now we have a solenoid. It's my representative solenoid, 32 centimeters long. Radius of 2.4 centimeters. And 40,000 turns. All right. So here, what I'm going to do is consider the very top coils of the solenoid coming out So if the current is coming out, actually I've drawn in, so we're going to go in to the page here. Of course, this continues because this is a long solenoid. And at the bottom of the solenoid, those same wires come out of the page, and that continues. And these do curve around like this. The cat is going after my wire again, so don't be surprised if the camera goes out, starts to move. Now my path I'm going to take, because there's a nice constant magnetic field within this solenoid, the path I'm going to take is down here, around, straight up, and over. And the reason for that is that there's a nice strong magnetic field, constant magnetic field near the center of the solenoid, but out at the edge here, the magnetic field is about 0. All right. And there's some other nice zeroing out effects that we're going to look at using Ampere's law on these edges here. Okay, so if you saw my previous video, you probably saw this. I'm going to do a repeat and put it in context of this question. So as we write out Ampere's law, and now consider the sum of the loop. This cat is clawing my legs. Why are you clawing my legs? Oh. Help! He's clawing my legs, going after this thing. Thank you, Golly. Are you going with Mom? Okay. Oh, that hurt. He definitely has sharp edges. Oh. Okay. So we're going to add up the length as we go around this path. Now let's say this little length right in here is L. We'll just keep that in mind, just a arbitrary length L. I'll zoom in a little bit so you can see that. Okay. So as we go from here to here, it's going to be the main part. It's going to be a magnetic field, a constant magnetic field, and that's a key for Ampere's law. Constant magnetic field times the length L. So if we sum up all that length, it's L. As we go up, all right, there's going to be this other segment. I'll call it the B on the left. Now this magnetic field is going to be changing quite a bit between here and here, but that doesn't really matter. If this length is also L, you're going to see here in a second, it won't matter. The B and the L, this B dot dl, they're in two different perpendicular directions altogether. B is perpendicular to L. 90 degrees separates them. So we've got a cosine of 90 degrees in there. If you take A dot B equals AB cosine theta is the definition of the scalar product, then we'll have a B dot dl equals BDL cosine theta, where theta is the angle between them. So there's a 90-degree angle between these two, and that's excellent because all that would be 0. It doesn't matter what this magnetic field is, there's 0 contribution to this left side here. Now if we go across from here to here, there's a 0 magnetic field over a length L. And finally, as we come down here, we've got this B on the right, whatever that is, times the length L, but there's also a cosine 90 there. All right, so the only component that is going to be really important here, the component of this closed loop, is the bottom. That's the only non-zero value. The rest of these zero out. So all that equals mu naught times the I enclosed. All right. So B times L equals mu naught I enclosed. We now have to figure out what this enclosed I is. Well, if there are n number of turns, say I got 4 here, then there are 4 currents. Okay? If each of these loops has a current I flowing through it, the cat is back. Come here, kitty. Edge, what are you doing? It's fun attacking my legs. He's been attacking my legs. Dude is sharp.
Yes.
He's fine. Sorry. So the I enclosed is n number of turns times I. That's the current, the total current enclosed there. All right. So now we can put all this together. BL equals mu naught times n times I. And back to the context of the problem, this has n number of turns and a length, 32 centimeters. Now we're not looking at this whole thing. However, that total length of the solenoid would give us a number of turns per unit length of any section of the solenoid. Mainly we want to focus on near the middle where there aren't those fringe effects. So we don't really have an n number of turns here because I don't know, out of those 40,000 turns, I don't know how many are within this section of my arbitrary length L. Therefore, if I convert this to something more like a number of turns per unit length, it's more helpful. So if I divide both sides by L, I get a mu naught I times n divided by L. And I'm going to call this n over L. I'm going to call it lowercase n because it'll have the same, ow, pain, monkey, edge. Come here, buddy. Oh. They're adorable until they use their little claws to claw your leg and open you up and slash you. Ew. There he is. That's Edge. Lots of cups of paper. Bye-bye. It's gonna jump off the table and attack my legs again. Okay. So this n divided by L will be our number of turns divided by 0.32, but that's the n number of turns per unit length, and that ratio is going to be whatever my arbitrary small little segment here, number of turns. This might be 4 turns per my, for a millimeter or so. Okay, maybe there's 4 turns in a millimeter. So that ratio is going to be the same for the large one or the small one. The ratio is going to be the same. So for a solenoid, the magnetic field is mu naught I times n, where n is the number of turns per unit length. So I'm ready to solve this now. N will be 40,000 turns over 0.32 meters. 125,000 ow, cat turns per meter. Hold on a second. 37.2 Teslas is our magnetic field. 4 pi times 10 to the negative 7 is mu naught. I is what we're looking for. And we're going to plug in our n of 125,000 turns per meter. And we get 236.8. amperes, and I really should use 3 sig figs. So we got 237 amperes. It's quite a bit of current. You can't really do that at home. If you wanted to use a circuit at home to carry 237 amperes, the 50 amp wires you get at home, really low gauge wires, they're rather thick. They're really large. To get 200 amperes, you need some thick, probably aluminum braided cable. And to get 125,000 turns per meter, that sucker would be huge. It'd be very heavy, very unpractical to get. Plus, you'd have to sheathe all of it. It's that kind of cable often comes exposed, not wrapped up in something like a plastic or some kind of insulator. So as MIT folks would probably have to dip it in something that's really cold. Liquid nitrogen might do it, something to give it some more superconducting properties. But there you see the challenge in producing large value magnetic fields with a straight wire. Would require very large current. Even just a couple of loops, 100 loops, 100 turns, it would still take a large amount of current. But that solenoid seems to be getting it done. So I hope this example is helpful in getting you through your homework and preparing you for your test.